Welcome everybody to this afternoon's lecture by Professor John Walsh, a third talk on the Irish ore deposits in a series of three. John is a founding director of the Irish Center for Research in Applied Geosciences. He's a co-director of the Fault Analysis Group in the School of Geological Sciences in Dublin, I believe.
Yep.
He's jointly funded by the SFI and industry, and he performs applied geoscience research in Ireland within a broad range of appreciation areas, including groundwater, hydrocarbon, marine, and raw materials industries. He's going to talk to us today about fluid control flow between within extensional basins and implications for sedimentary rock-hosted mineral deposits, which has lots of applications all over the world, I'm sure. So John, with that, please take it away. Go ahead.
Thanks, Craig, and thanks for inviting me, and thanks for everybody attending. So what I'm going to be doing is, oddly enough, is I'm actually not really going to be talking about the Irish zinc-lead ore field. I'm going to be talking about faults in a generic sense. So these are aspects of geology, faults, which you can more or less sort of use the world over. Having worked on faults for so long, whether it be within hydrocarbon, coal, minerals, or you tend to get a sense, at least, that faults and an understanding of them can be used from one application area through to another. And some of what I'll be talking about will be impressing this. The group is, the work is the group of people shown here. It's mainly from ICRAG, from UCD. And I should say also that there's a download button here. You can get this paper, with a paper which more or less ties in very well with this talk. And that paper is available free to download from SEG. And if you all do it quickly, because it stops being available for free in June. So this is what I'm going to be talking about. Okay, keep on. I'm having people coming up into me, and I cannot advance this. How did we do that? Yeah. So we're going to be talking about fault control, fluid flow, and sediment-hosted mineral deposits. I suppose one thing that I would like to impress is that normal faults, of course, and I'm biased, are important, and they can have a profound effect on fluid flow within basins. They were a curious sort of behavior in the sense that they can actually be barriers to fluid flow, and they can also be conduits to fluid flow. So they've got a little bit of a schizophrenic sort of thing about them geologically. They can do more or less what you want them to do. And I'll be impressing on that the notion that a fault can be a barrier and conduit at one and the same time is perfectly plausible and tenable. I'm going to consider this duality of flow behavior and its impact on flow within sedimentary basins. And then we look at the applications of these processes and models to a variety of things relating to fault-related fluid flow from mineral deposits. So what I'll start off with is really something quite generic. I'll be talking just about faults. I'll be using examples from different sorts of systems, but it'll be about the fundamental processes associated with faults. Here's a basin, we're extending it. And one of the critical things that happens within a basin when it's extended is, of course, it's faulted, but also the crust thins. So you can see that this crustal thinning means that the mantle, which is the hot, that's the source of heat, that upwells and the whole crust is heated up. And in so doing, in heating up the crust, then it starts to get fluids moving within that crust. It's basically, I suppose, the cooker underneath the crustal extending crust, and it starts to get fluid flowing. And so here, for example, or taking a blow up of this diagram, we can end up with fluids which are within the pores of the rocks and sedimentary basins, and they can start migrating. They're heated up, and they can start stripping out they can start stripping out fluids and in particular chemistry from the underlying rocks, whether it be the sediments or the basement below. And these minerals, scavenging these minerals, they can end up in solution. They'll have to escape because they're being heated up, they're getting overpressured, and they can heat up and go along faults. So you can have migrations of these fluids up along faults, and sometimes you get a replacement by the minerals are replacing the country rock along the fault. Other times they start to trap against the fault surfaces, a bit like hydrocarbon fields as well. And you get trapped columns of mineral or columns of oil by virtue of the fact that the faults are the best way up. If you've got high pore fluid pressures, the faults end up being the way to tap into them. But you can see that at the same time, we're actually trapping against the faults themselves. So it's doing both things. Where do we get the fluids from? Well, they'd be within the pores in the country rock, but also they can be fed into the system. Some people, for example, consider and talk in terms of heavy brines, cold, heavy brines, and they can sink through the crust from either outwith of the basin, outside of it, or even along the very same faults that are locally pumping up fluids could in fact be sucking down heavier briny fluids, and they can sink then to depth, and eventually they get warmed up. They will start to actually sort of strip out metals, and then they will start rising. So what I'm going to do is I'm going to, oddly enough, I'm going to start off with a dead basin. This is a basin which is tectonically dead. It's in the North Sea, and it's on our shores, and it's actually a basin that died and stopped in the Upper Jurassic. So it's over 100 million years it's been dead. And what I'll show you is, though, something can be tectonically active and the faults won't be actually moving because of plate tectonic movements and crustal stretching. But the faults have a life. They have a life in fluid flow, which is much older and longer than their life when they were actually moving, because they're there and they can end up being and affecting fluid flow. This is a part of the North Sea, the North Viking Graben, and you can see the deep here. These are the deeper parts of the basin. The basin's been stretched about 15%. It's probably not too different from the East African Rift, I think, but there are people who are more expert on that. It's not a very great deal of stretching. But the effect of it is that we end up with lots of faults, and you can see the faults in the Jurassic sequence here. And because the faulting was Upper Jurassic times, in fact, the faults really outstripped the sedimentation in their movement. And you can see that the Cretaceous is just ponding into the holes to the bathymetry that the faults left behind. The faults were moving too quickly for the sediments to keep up and to pile in. So the Cretaceous came later, and everything starts to subside as the whole system cooled. Then the Paleocene, the Miocene, and so on comes over the top. We end up in a conventional basin, and that basin is tectonically dead. But the same basin, and people have done modeling, that a lot of the hydrocarbon movement and the fluid movement is basically happening today, potentially. So the migration of fluids like hydrocarbons has been happening much more recently than the faults were being active. This is a system affecting fluid flow just by the faults being there. And you can see that the faults are actually trapping. They're trapping oil, and this is schematically shown for the hydrocarbon. But as I'll show you, we can show that the faults, they trap hydrocarbons. They must be pathways to hydrocarbon migration, because it's only in the depths of the basin that things are hot enough to actually start generating hydrocarbons and gas, for example. So we have to be quite deep, and yet they're migrating upwards to be on the basin margins. So there must be conduits, and I'll show you that there must also be barriers to fluid flow, to pore fluid flow within the basins themselves. This is a hole, or this is actually showing what you would get when you actually drill holes down and you measure the fluid pressures, the pressure of water within the pore space as you go down deep. You can drill down, you can do that for lots of wells, and this is showing data here from the North Viking Graben. And if we were to say that the fluids were open to the surface, then the pressure of the fluid at a particular depth is predictable. It's just one column of water, and it's got a particular density. And we can take a curve and say, well, actually with depth, the pressure of water as we get deeper will increase in this way, along what's referred to as the hydrostatic gradient. If, on the other hand, we're looking at the pressure of rock, because rock is obviously at least 2.5 times, oftentimes denser, then the ramping up of the pressure, and this is pressure on the upside here, the ramping up the pressure is much steeper, because the rock pressure we're talking about here now it's the lithostatic gradient. Now, in practice, in fact, the pore fluid pressures, the pressures within the pore fluids, within these basins, they're not actually either fully hydrostatic or lithostatic. They actually start to ramp up. And you can see when they start at about more than about 1 kilometer, up to 2 kilometers. What happens is that the pores, they're between the grains of sand, for example, they get compressed so much by compaction, so you put more and more sediment over the top, that the pores start to become disconnected, and the fluids between those pores starts to ramp up in pressure, really it's locked in. That's the isolation depth. That's where the pressures really start building up. And you see these pressures? They start building up within the rock. And that buildup of pressure here is overpressuring. There's basically fluids in this rock, and they've got a pressure to them. Now you see you can see how they ramp up here, but they never actually get to lithostatic. You know, this pressure where effectively, if you've got a fluid which is under lithostatic pressure, then it supports the whole rock column. They never get to that. And the reason they never get to that is because of these purple pink points. These are tests. These are tests that people do to actually, or companies do, to work out what pressure it takes for the rock to fracture. It's like a fracking, really. But it's not what they're intending to do, but this is what happens here. This is the pressure which the rock starts to break up. And when the rock starts to fracture, then the fluid pressure diminishes. So these fluids in the oranges might want to get to lithostatic and be totally closed in and have the weight of rocks on top of them. Sorry about that. They might want to have the weight of rocks on top of them, but in fact, they never do that because the pressure gets too high and the rock reaches, effectively, it's a hydraulic gradient. It's a fracture gradient, the rock fractures. So today, the rocks are fracturing in the North Sea and they're bleeding off the pressures so that they don't become lithostatic, which is just as well, because if they did, then they'd blow the top off drill rigs which were drilling in them. So you can see it's a dynamic system. But the actual buildup of pressure depends on where you are. And I'm going to show that because faults are really critical to this. This is a pressure map of the fluid pressures within rocks of a particular age. It's the fluid pressures of those rocks, or the fluids within those pores. This is 100 bars is the pressure. That'd be equivalent to 10 megapascals for those of you who are familiar with that. It's low pressure here in white. So that's in this area here. Yellow, higher pressures because we're getting deeper. Pink, even higher pressures again. So within the basin, there's very high pressures. They're overpressured. And it's basically, this pressure is pushing fluids out of the basin. And this is one way of driving a flow up the faults, for example. But you can see where the compartments are happening. You can see where the faults and how they play an important role in this. These are all of these pressure compartments are all fault bounded. The faults are basically defining the pressures. Somehow they're actually slowing down the flow and generating compartments. We can take it a little bit further and we can get closer here. And this is on an even smaller scale in this little box. there are compartments to fluid flow here. And those compartments are very clear. All fault-bonded compartments. A basin, it's dead. It's a dead basin, but it has a really dynamic fluid system. This is more than 100 million years after it was actually tectonically active. And we can look even closer and we can see that it's fault-banded again. I'm going to look at this little red area here. And in that red area, this is a 3D diagram which shows the top of a particular unit. And you can see the faults, I think, here. You see where the big drops happen? These are faults dying out along their length. It's called a relay ramp here. And the amount of extension at this end on the left-hand side, which is, I think it's about 40 kilometers across the area. The amount of extension on the left is the same as on the right. We're looking towards Norway as it's further, and we're in the middle of the North Viking Grab. If you look at the pressures though, the pressures are directly linked to the faults. The overpressure, the amount of pressure in excess of what we would have if we just had open water, is 300 bars or 30 megapascals. It's high in the basin, it decreases across this fault block, and it decreases across this fault block. There's a wave, there's a pressure of fluids which are actually out of the basin. It's a dead basin. But the faults are obviously letting the fluids out, but they're also holding them back somewhat. And we know by the hydrocarbons, they must be coming, the fluids from hydrocarbons must be coming from depth. So we got a conduit and barrier situation. Why does that happen? Well, in the North Sea, a lot of the rocks that we're talking about are actually sedimentary rocks, siliciclastics, so they're clastic sequences. This is what we're talking about, sedimentary-hosted systems. And if we look at the fault zones, the fault rock that we actually get along the fault, and we plotted clay content here on the upper axis, and then here on the left-hand axis, if we look at depth of burial, we got very low clay content over here. It's very sandy sequence, hardly any clay. There's really not, and it's very shallow depths. There's not a lot happening there. The grains roll. We got sand on sand. If we get down deeper here with just sand on sand, we get things called cataclasites. The details of that don't matter. All that happens is that the grains are crushed in these sands, but it's a sandy rich rock because the clay content is low. On the other hand, when we get to high clay contents, you can see in this picture here from, this is a picture from Sarawak and Brunei, an outcrop picture. You can see these clays are smeared down the fault here. Beautiful smearing happens. That means the fault rock is basically clay. There's a lot of clay in it. If we take this other example, which is at a deeper depth, that was relatively shallow in Miri and Sarawak. If we get into a deeper depth here, these are actually consolidated, lithified rock, it's sand, but even then, it's a soft material here for clay smears. The shale smears, it's hard, but even though it's brittly deformed, you can see there's actually clay all the way down it. So we can get clay along faults in lots of ways. And that's important because if we have a fault with increasing displacement, we expect to get fault rock within it because that's what happens. The host rocks is broken up either side of the fault. And here's a plot here which shows thickness against displacement. And this is for fault rock. And can you see that as the displacement on a fault increases, and that might sometimes be as the numbers of earthquakes happen on a fault increases, then you get more and more fault rock, and the fault rock starts to broaden. And that fault rock, if you're in a sand shale sequence, it'll have shales in it. And the shales are going to act as a barrier. Yeah. So we can end up getting proper hydraulic effects. Here's an example of one such fault. This is Taranaki Basin in New Zealand. It's a 30-meter fault. The right-hand side has gone down. And this is a fault zone. No fault is a perfect plane. It's got multiple slip surfaces within it. These sediments were at about 1.5 kilometers, maybe 2 kilometers depth when they faulted. And at those depths, they were not really solid, they weren't really lithified. We get beautiful clay smears developed along them. And I'm gonna show you that. There is some cataclasis here. And so this is a blow up here of an example just down here. And you can see it's gorgeous, lovely. Look at that, down the fault. See the smearing of the clays? Even these little minor Riedel shears have little smears on them. Gonna get a little bit closer. This is another one. See beautiful smears down here with Riedels cutting across it. I brought some sedimentologists to this, and these are lovely turbidite sands. And then you get a fault like this, which you wouldn't even see on seismic. And it frightened the life out of them because you get lovely sheets of sand. You get these faults, which are really basically just, you can't see them from seismic. And they make mincemeat of the flow because these will act as barriers to a cross fault flow. Very hard. The permeabilities of these clays is, for those of you who are familiar with things like this, is 2 nanodarcies. And that's tight. You're not going to get anything flowing through that, 2 nanodarcies. So that's 2 times 10 to the power of 9 darcies. Yeah. We can even look at rocks which were lithified. So they were proper rocks when the fault happened. Here's a normal fault. And I should say, I'm always talking about normal faults. I mean, that's what the title of the talk is. And all of these examples that I'm looking at are faults within sedimentary, normal faults within sedimentary basins. This block on the left-hand side dropped down. It's dropped down by about 15 meters. You can see this little sketch. There used to be an 8-meter thick shale above on the right and below on the left-hand block. And you can see that it's full of shale. This is all fragmented shale, but it's still shale, it's still tight. In fact, if we look at it close, some of these faults, you can see here, do you see the clay-rich fault rock is smearing up the fault? And yet this is fragmentation. It's not a soft, this is not a soft material. It's cataclastic. And we end up with these smears developing. So what we can actually show, and people have done this, they've measured the properties of fault rocks, the permeability of fault rocks relative to the clay content. So that's shale. If you're talking about a rock, it's clay minerals, which are really the impermeable materials, these things coming down the fault. The sands are fine. You can see that as the clay content increases here in the bottom axis, you drop, the permeability drops, and then it becomes really low when you get to a fault rock, which is about 40–50% clay. This is a rock which has faults, this is a minor fault here, which is about 50% clay. It's really very low permeability. So we can sort of predict these things, and that's what people do for reservoir modeling in hydrocarbon world, or for trying to predict traps. The most important thing is that faults can seal if they're in sand and shale sequences. So here's forget about those ones on the right. Here's a sort of a model of an oceanal fault. It's got a fault zone, it's got fault rock, it's got clay-rich material when it offsets clays, and it's got all sorts of fault lenses and so on, the likes of which we'll talk about in a second. Yeah. So one thing we need to talk, I've been talking about within sandstones, it's self-evident, I think, that if you have a fault within a tight rock, so you've got a fault within a rock which is basically no porosity in it. That fault, if it moves in it, it's going to break up the rock. And the rock will be break up, and those fault rocks will be more conductive than what the tight rocks are. Take a fault in basement. It's nearly by definition more conductive, at least when it's moving, than what the surrounding rocks is. So faults can be conductive. Faults can be impermeable barriers. In impermeable rocks, I should say, they can be pathways for up and down fault flow. What about faults within these clastic rocks, these layers of sandstones, which themselves are permeable? So they allow flow already. What happens is that the faults end up being impermeable or more of a barrier. Yeah. So we'll end up trapping pressures, just as we've seen in the case of the North Sea. Fault rocks in clastic sequences, they'll have a permeability which is relatively low compared to the nice sandstones, and so they'll act as pressure compartments. But in fact, oddly enough, those same faults will have permeabilities oftentimes. The permeabilities will be greater than the vertical permeability of the sequence. So if I stack the sequence, sands and shales, and I work out the vertical permeability, how long would it take me to actually go vertically through without a fault? I mean, it's pretty tight when I get my continuous shales. But if I put in a fault, I mean, the fault may have a permeability which is low and it stops cross-fault flow, but it will allow up-fault flow because it's still the best way up. It's better than not going through a fault. So a fault can be a conduit for up-fault flow, and yet it can stop and act as a barrier to cross-fault flow. It can do both things. So effectively, depending on the context, the self-same fault can act as a barrier and a conduit, depending on its cross-fault flow or up-fault flow, and depending on if the fault cuts tight rocks or porous rocks, it can do the opposite too. So it can do what you want. And that basically means that it's not just an on-off switch on these things. I'm going to go through now some of the models for fluid flow associated with faults, the classic models. This is a fault valving model. And what this model does is it takes a fault, and that fault here is going through here. There's a layer which is very tight. It's sort of a barrier to flow. And that layer effectively transects the fault. You can imagine if you looked a little bit closer, you could probably, I think Lindy Fryer is having a problem getting in and out here. I don't know if you can hear the chimes. Anyway, I'll persist with this. The box keeps on coming up on my screen.
John, I keep trying to let her in, but I'm not sure what's happening. So
yeah, I don't think she seems to be having a problem probably with her
she may
maybe
have the
connection
wrong
or
code,
something like that. Yeah, that's fine.
Just carry on.
Grand. So we have this barrier. This is a fault. Yeah, and that fault is coming through. And we got an impermeable barrier. And what happens is that between movement on the fault, we start to get pressures building up underneath this impermeable barrier. Above it, it's hydrostatic. So like the pores are open to the surface. Below it, start to pressure it up. What happens then is that if we look at our pore fluid pressure curve, remember it's hydrostatic, then it increases and it's going to a position like this. If the pressure builds up more, do you remember it hits this fracture gradient that the leak-off test told us happens. And what will happen is that we'll valve fluids up the fault and to re-equilibrate the pore fluid pressure profile so it's not too overpressured underneath that barrier. That's valving. Fluids are burped. It's a bit like burping. Get a bit of pressure on and you basically valve it off along the faults. And faults are very convenient from that point of view. Now, Simpson presented this model, but in fact, Phillips presented a model which is very similar and in the context of minerals. This was the Walsh ore field here, and he envisaged that you have pressure buildups and you can end up valving, in this case, zinc-lead minerals up along the fault, and they will basically valved into sort of a halo, a mineral deposit higher up along the fault surface itself. Here's our impermeable barrier going straight across, and we're sort of valving fluids through that impermeable barrier to produce these along the fault surface itself. Now, what Phillips did is he sort of looked at the stresses associated with a system like this. And without getting into the details, what he was able to sort of show is that effectively what's happening is that the stress, the pore fluid pressure, builds up so much that the rock is driven to failure. So it's like a geological fracking. This is a natural geological fracking. And all the fancy things that that does is here. It's shown on these Moore circles, and you don't have to worry about those. But effectively what happens, depending on the stress conditions, is we will get valving of fluids up. Sometimes they'd be along the fault itself. Sometimes they'd be on vertical fractures. The details don't matter. What is important though, is that you can see here, the amount of fluid that we can move along a fault is many cubic kilometers of fluids over the entire lifetime of a fault. In fact, it's arguably, it's many cubic kilometers beyond the lifetime, the tectonic lifetime of the fault, because this is just burping fluids. The fault isn't sheer movement. It's not an active tectonic zone, just fluids are being valved up. Small little burps. There's another mechanism, which is seismic pumping. And as you can imagine, it sounds a little bit more active, and it is. What happens is that when a fault moves, it has an effect on the strains within the rock surrounding the fault. And this deformation, you can see sort of, this is a big fault. It could be kilometers, but faults always die out. Their deformation always dies away from them. So there has to be deformation in a fault that dies out. Faults have to die out, because if they didn't, the world would fall in half. If you look at any proper detailed configuration of faults, you'll see that they die out laterally and so on. When we have a buildup of stress, so we have a flat surface here, and we start to sort of bend it because we want, this block is going to be moving down in this extension. We're extending the fault and we're bending the bed, and then that's an earthquake. We get the bending of the fault, we get a flip. Before then, the layers are bent. We have a sort of like an elastic bending. And also this layer is being stretched because the basin is in extension. It's a sedimentary basin. It's got a normal fault. What happens is that when it extends, it sucks in fluids. The pore fluids are actually, pore fluid space is increased. Fluids get pumped into this extended part across the fault before a seismic event happens. And then an earthquake happens, ping. All of these spaces are all compressed. This is what happens in an earthquake. In this particular case, it's the Bora Peak earthquake. It's on the Lost River Fault and Basin Range. And this is what happened in one earthquake. The side of it, here, this is the footwall side. The upthrown side goes up and the hanging wall side goes down. Here's the fault. You notice the scale is millimeters ups and down, and this is 10, 20 kilometers. So it's a small up and down. But if you do this thousands of times, you end up with a really big fault. And that's what happened here. This is the Bora Peak fault. This is the time averaged. This is the picture, the geological picture. And you can see that the footwall here on the right-hand side is really going up and the hanging wall going down. The deformation and the balance of it is different, but I'm not going to get into that. But the most important thing is that when this earthquake happened in 1985, do you see this Thousand Springs Valley? There's a reason it's Thousand Springs Valley. It's because what happened was when the earthquake happens, springs are developing. What happens is the pores are collapsed and squashed when this earthquake happens, and the water is expelled out. And this is a modeling of that. If we take a fault of this scale, and this is Bora Peak scale here, an earthquake, it was about 1 or 2 meters displacement. This is another one. I'm going to show you the real data. These are the numerical curves which say if the top 2 kilometers has a lot of porosity in it, and we look at the strains associated with them, then this is the excess flow that we're going to get close to the fault. Here's the fault here. So a lot of the rocks are going to be squeezed just when this normal fault moves. It'll be squeezed and we squirt out fluid. If down to 5 kilometers, we take the strains associated with that, assuming that the material can easily be compressed, 5 kilometers, 10 kilometers. This ends up being a lot of fluid. Here's a map here. The whites are compression. During this earthquake, all the material here on this fault, all the material is compressed at the time this earthquake has happened. What happens is that a whole pile of springs start. When this earthquake happened, lots of springs appeared. and huge volumes of rock were moved. This is the real data, and it's not bad. It fits in with the curve, the predictions quite well. The predictions come from a theory called elastic dislocation theory, but it doesn't matter about that. This light green here is a bit off, and that's because it's a step in the fault, a little bit complicated. But here are the main Bora Peak and Hepkin Lake. These are two earthquakes. Fits nicely. Lots of fluids coming up. In fact, you can work out theoretically that the amount of fluid which is actually coming up here during the lifetime of a fault is 1,000 cubic kilometers of water. Now, lots of people agonize and worry about where do we get all this water that's going to flush around to get metals out. This is a model which can do a lot for you. So we talked about valving, which is burping, which in principle could happen within a basin which is tectonically dead. This definitely requires seismic activity. What happens along the fault during earthquake events? And we look at another model. This is a model called seismic pulsing. Again, it's when an earthquake's happening. It's not valving, which needn't have an earthquake. What happens during a rupture along a fault, because the fault is irregular. If I move my hands here, I don't know what I'm doing, that's a demonstration like this, but if my hands are irregular, but they're a fault, if I move them, you can see that openings start to appear. I get dilatancy. You have to open along a fracture or rupture, an earthquake surface which is moving. You have to open it, dilates. And that generates space and it sucks in fluids into it. And then as the rupture passes up through the crust, that sucked in fluid moves up. And this is how the progression happens with this particular model. This is the notion that this is the pulsing. It's just showing like this little triangle, which is an area where the rocks are sucking in and dilating, and it passes up. It passes, in this case, past a hydrocarbon field. This is a hydrocarbon trap, and it carries this hydrocarbon up upwards. So effectively what's happening in this case is pulsing is causing a hydrocarbon trap to leak. Now, it could easily be ore-bearing fluids, but in fact, in this case, it's hydrocarbons. And it's important because you leak off entire reservoirs. Because this is a way also of getting movement up faults. This is a fault that's trapping, but it's still valving, it's still pulsing during movement. It would even valve if you increase that oil column too much. This is the amount of leakage you get. You can have a look at that in the paper. Do you remember that paper I showed a link to? You can get that now. Up to 100 cubic kilometers over the lifetime of the fault. So between seismic pulsing and pumping, you're in business. There's lots of ways of moving fluids. And you can still do it when you want to valve a system. So there are ample ways, really, given all these different models, which we've sort of pulled together into one paper recently, to get fluids going. But what about the faults again? I'm going to get back to this. This is the plot of thickness against displacement. And you can see these are on a logarithmic plot. As a fault gets bigger displacements, it gets more fault rock. Now, it's on a log-log curve. This is a log-log, and that covers a multitude of sins. It's very forgiving. But we have to plot them. We've got faults here with displacements of up to 10 kilometers. Yeah. And they have fault rock thicknesses of a couple of 100 meters. So we have to plot them because these are really small faults down this end. But the most important thing is, do you see the range? There's a lot of variety along an individual fault. There's a lot of variety and variations in the fault rock thickness. Some places it's thicker and some places it's lesser. And we're going to talk about why that happens, and it can vary rapidly. I'm going to look at some of the processes. So here's a fault. It's never a perfect plane. This fault has an offset of about 20 meters. So in fact, it's offset the entire sequence down on the right-hand side. So by about the height of the cliff, yeah? A beautiful fault from Greece. And you can see it's got two main slip surfaces, but it's got multiple internal ones. This is not one surface. The fault is complicated. It's got lenses in it. it splits up the displacement. And we'll talk about that now. This is happening because we get segmentation on faults. And Kuhn yesterday talked about segmentation on faults. And you can see this is a fault here on a bedding plane, which is dipping towards us. The movement is perpendicular to that bedding plane. So it's like a normal fault. You can see it's got a big displacement here, and that big displacement is dying out to a tip here. The fault is dying out, as you'd hope it would sometime. But in fact, it's segmented. Can you see that it's actually got steps on it? Yeah. And those steps, do you see close up of that step? There's a ramp. The beds are rotated. This is called a relay. In all likelihood, these segments, they probably join in to be exactly the same fault just below and out of the plane that we're looking at on another layer, maybe 10 meters below. Yeah. But at this level, it's split up into two. Splitting and segmentation of faults is standard. If you want to propagate a fault through a layer of rocks, it's very hard not to get it segmented. But these segments work together. And so they transfer displacement between them with a relay ramp. You increase displacement, it breaches. It's a breach relay. You see here, this relay ramp here is rotating. And do you see this cracks going across it? It's a relay about to go. It's about to fracture, break. If you take it further, it can become doubly breached as displacement increases. So how does this relate to fault rock? Because I'd look at this and think, well, actually, when that relay ramp breaks up, I'm going to get a lot of fault rock there because the relay ramp is going to be pulverized. And that's what gives you variety. The original segmented and also irregular nature of faults, you know, the way faults have bends and all sorts on them. That makes fault rock vary. But these complexities are the locus of fracturing. There's lots of fracturing where you get complexities. And this brings us to a model which we presented in 2009, which is a geometric model for faults. Here's a relay ramp. Here's a lens. There are damage zones. So these are like fractures either side of a fault. And then there's fault rock, which is shown here in black. This is quite an involved diagram. Don't worry if you don't get it. You will if you could be bothered having a look at the paper and seeing it, yeah? This is displacement and thickness. Do you remember this? The black is our fault rock. If I plot an intact relay, so a relay with a proper ramp, and I think that Kuhn touched on this yesterday, take the separation of that relay ramp and its displacement, all the intact relays plot here in red. They're to the left and above the fault rock. If I take breached relays, you can see they're orange. They're just about to the right. Doubly breached relays, some of those are definitely off to the right. These are lenses now, and then the fault rock is here to the right-hand side. How do we reconcile these things? Well, the way we do it is this. If I take a fault, whether it be an outcrop, this is an outcrop, it's only got a 10 centimeters displacement or something at it now. Beautiful relay ramp, do you see it? You could go up that ramp easily. This is a 45-meter fault from seismic data. You can go up the ramp and so on. But you can see this ramp is about to go. So if I increase displacement from this point, which is where this plots, it'll start to migrate to the right. Displacement's increasing. The separation of a relay doesn't change. Still the same relay. All that'll happen is that the stuff in the middle will end up being broken up. And it starts to migrate into these doubly breached blues things and then into fault rock. And eventually it will become fault rock. And that's what sustains this displacement thickness curve. You can't get thickness increasing unless you bring host rock and more of it into the system. That's exactly what a relay does. You get this host rock and you start to pulverize it, and things migrate and can migrate with increased fault rock thickness and displacement through time. But it's being fed by relays coming in from the right and complexities. Here's an example, a real example from Moab. This area is very similar to, there are actually some deposits along its length. I'll show you in a second, very small. So This fault has a displacement of about 1 kilometer in the south, and it decreases upwards or to the north. When we get to low displacements, can you see this fault is not a discrete fault. It's got relays in it. At low displacements, the relays are there. If we go further down the fault to where the displacement is nearly 1 kilometer, 800 meters actually, do you see we don't get relays? We actually get lenses. And those lenses are critical because they're really deformed. They got lots of fault rock. I'm not going to get into the details of it, but you can imagine getting pulverized. If you take something like this intact relay up here and you increase the displacement, then you link them up and it ends up being that. It'll end up being ground up, broken up fault rock. And what will the broken up fault rock do to you? It's a pathway. It's quite a convenient pathway for upward fluid flow at the very least. And of course, that's what happened in this case. These are mineral shows, copper, iron, and hydrocarbons. And lots of them are associated with these relays, these branch points, the points where the relays link and you breach. When they breach, at that point, it's called a branch point. And that is a line that goes down with depth. If you want to get hydrocarbon or minerals up, that's a way to do it. And here's nice hydrocarbons here at this branch point and so on. So along this fault, it's a very long fault, 45 kilometers. There are places where there's mineralization. When we look, we can see complexity of fault zone structure. That's where the sweet spots are. I'm going to show you by illustration an example of a fault from Malta, very well exposed fault in Malta. It's a 1 kilometer scale bar. The top is to the north. Well, actually, it's not to the north, it's to the south because I've turned the north arrow. But the top of this diagram here is going down. That's the hanging wall side. And here's the fault. Yeah. We're just going to look at a few different spots along that fault. Most of the time, it's pretty boring. It's fairly planar. But when we get to these complexities, see this big bend there? We think that bend is where there was a relay. It used to be segmented, but now it's actually linked. And in fact, there's probably a fault going through here, but it's in the sea, so we can't see it. If we look at that, we get these beautiful lenses. Gorgeous. This bend is taking a hammering. See all these lenses here with broken up fault rock? The bend on this fault is basically being eroded. It's an asperity, it's an irregularity, and it's going to be eroded by multiple slip events. If we look at this intersection between a fault here, a minor fault, and a major fault here, this is all part of the same fault. And you can see it, this has bends in it. These would have been originally relays. Intersection, and here it is here. This is the fault, the beautiful polished surfaces. And look at this. This is where the fault comes through, this minor fault. Breccia, fragmented host rock. It's in bits. So this brecciation here is a really good way of generating fault rock. And fault rock is a really good way of transmitting things up along the fault from depth. And here's a relay ramp here, over here on the right-hand side. There's a relay ramp developed, and you see this is the back main part of the fault here, a map view. And on the back, this is it here on cross section. There's the back fault. This is the hanging wall fault, and this is the relay ramp. It's in bits. It's broken up. I think it's we worked out there's 100 times as many fractures just in this little area as there is along a lot of the length of the fault. This is a sweet spot in terms of fractures. And we can show that with these little bubbles. These are in proportion to the fractures, fracture density. There are just some places where there's a lot of flow coming up a lot of it because it's damaged. It's structurally complex. And that's what we see in mineral deposits as Kuhn was talking about, and I'll touch on a bit later. This is just to give you a sense of the flow associated with just a little relay. Do you remember these ramps? These are different layers. This is a ramp. If I do a numerical model, and this is injecting fluids here, red, and producing them blue, the minute I put in a ramp, which connects up layers, I start to get a vortex of flow lines. It's a great way, complexity of structure, the bending of the beds, the breaching of the relays is a great way of connecting things up and to get fluids. Ultimately, they generally move upwards, of course, because that's the way of the world. So we'll get, with relays, they become breached and we get tubes of fault rock. I haven't talked about this, but where we get bends on the fault, refraction, because the fault is refracting through different types of layers, we'll also get bends on a fault, and they'll also be broken up, and we get tubes in the horizontal. And these ultimately are going to be the things which could be the passageways, the conduits for fluid flow. And this brings us to the Irish mineral deposits. And what we have here is Lachine, and I'm not going to labor this because you can look at Kuhn's talk if you haven't seen it before, but these are faults with different segments, and the flow is coming up along those fault boundaries. We can see there's a lot of complexity with these faults. The mineral comes up the fault, it hits the layers here. In fact, this fault stopped moving. This fault wasn't moving when the zinc and lead was coming in. You can see that that goes straight across. This is a fault which was dead, but it still was the conduit for fluid flow of zinc and lead. It was a conduit during its movement for other mineral species. So it comes up along the fault, goes into the hanging wall and footwall, but it's coming up along complexity of structure. Here's our segments. I know Kuhn's shown you this. The purple is the deposit. And the center of the deposits are where these step happens. Wherever we have the main little ore bodies, we get complexity of structure. And that's where things are going to get hammered. That's where the rock is going to be. And this is a 3D equivalent. So segmentation is a great way of concentrating. And here's a few. I think these are all now available for download. Two of them are in economic geology, Kine et al. And Termans et al. And Walsh et al. Is the one that's available until June to download. Yeah, gorgeous. Look at the relay ramp. My father would say you get up in the middle of the night to look at that. I mean, that's a gorgeous thing, isn't it? Where the beds are ramping and displacement is transferring from one to the other. Each segment has its own little mineral deposit. And each segment has bends and complexity, which actually allow the fluids to come up into that segment and that mineral ore body. What I'm going to do is I'm going to finish off now with a handful of a few slides just talking about some generic aspects of fluid flow. This is just to be controversial, I suppose. Syngenetic versus epigenetic. People oftentimes used to think that the fluids were coming up when the sediments were being deposited. But I think epigenetics is probably becoming more in vogue. Certainly in Ireland it is. The deposits are considered to be epigenetic now. So they post-date deposition. We might have faults with sedimentary growth across them, changes in sequence either side of them. And this is the Mambashi in Zambia, and this is in the Selwyn Basin. These are sedimentary faults, but then actually the minerals are coming in later. It's below surface when this is happening. This is entirely post-dates, that half graben in Mambashi. So think more epigenetic. What about synth faulting and post-faulting? People are inclined to think that faults, they must have been moving to conduct fluids. They don't need to be moving to conduct fluids. They're just the best way up anyway. And here you can see continuity, the minerals, and also if you look at the fault rocks themselves, you can see that there aren't indications that in this particular deposit, Lachine, that the fault was moving. Now, of course, this is a small fault which might have died within a basin that's still active. It's still churning around the fluids, but this local fault is not moving. This mineralization is post-faulting. This is post-faulting. This is the mineral massive sulfides, and the faults are here, and the sulfides just go across it. Here's an example here, Brazil, in which we suggested, in fact, all the mineralization is probably post-dates all of these faults. But the faults are still part of the plumbing system, despite the fact that they're not moving. They're still conducting, and they're still providing traps. And the idea that faults can control fluid flow after they've stopped moving, that's standard in hydrocarbon world. In the hydrocarbon world, it's very unusual to actually get traps developing during the actual active time of a fault. Most times the hydrocarbon is generated after the basin is dead. And this is an example here. All of these faults are dead and we're getting lots of traps, and we obviously have to conduct the fluids upwards, which is what's happening. So that's fine. Post-faulting is grand. It doesn't have to be sin. What about sealing and conduits? It can't be both. You can see we're trapping here locally, but it's a conduit, this Lachine fault. And these are tight rocks. These are limestones. But here's another zinc lead deposits here within a fault here, which is a shale smear on it. And this is from the Eastern Irish Sea in Britain. A mineral deposit, lead and zinc. And here's all the mineral on the footwall side. So minerals come up along this fault on the underside of the fault, and that's where all the mineral is. It can't get through the seal, but it uses the fault to get up, even though it can't go across the fault. And by the same token, at the same time in another area, which is lots of limestones, we had refracting faults going through these different layers, and the faults were conduits to fluid flow. This is a conduit in a different way. It's actually a barrier, but it actually ends up channeling the flow. And here are the faults. Here's the faults with mineral along them. Faults with mineral on them in both cases. Faults are they're conduits to fluid flow, even if they're seals for cross-fault fluid flow. So I'm going to finish off with that. These are all generic sort of messages of how it is that faults can basically do an awful lot of what it is that we need them to do today. They can get fluids moving. They can cycle them, they can be the locus for a mineral deposit, or they can trap fluids for mineral deposits. And so I think I'll stop with that and take any questions if there's time for them. Okay?
Thank you very much for that, John. It's a new view on faulting for me. And mineral fluid flow. I'm sure there are some questions and comments. Brent?
Brent.
Oh,
Brent.
Man, you need to unmute your mic.
Mm-hmm. Oop.
Okay.
Brent.
There you go.
There.
Thank you for, oh yes, I had to unmute, sorry. Thank you.
Yep.
Go ahead, we can hear you.
Yeah, I have a question. You talked primarily about vertical conduits and faults and that. At Lachine and the other Irish deposits, there seems to be a lot of cross-contact mineralization going on. I know it's primarily related or looks to be primarily related to the conglomerates, but you have some sort of associated horizontal fracturing that's going on to distribute mineralization so far away from these.
Yeah, that's a good question. In fact, if you take the Irish deposits and you look at a cross-section of them, for example, you can actually see that there's these hydrothermal breccias, which are the sort of blocky things here. They're slightly different shaded yellow there. In fact, they predate the mineral deposit. And what we think they are to do with, and they're associated with, is at the early stages when the fault was moving and we were getting fluid flow at the same time, generally it was magnesium at the early stages, then producing dolomites, and these are hydrothermal dolomites and breccias. And they are those here. And there was also iron is the first sulfide phase to mainly come through. And then the mineral deposit, the zinc and lead is generally on the later side of things paragenetically. But this surface here, we think, is because we're at the base of a reef. It's a major mechanical boundary. And when the fault moves, then the layers, and if you can look at this, if the layers bend over, as they will do you see the way my hands start moving relative to each other? I get bed parallel movement. I get localization and deformation. So we think that's probably what's happening. We're getting laterally extensive sheets of breccias associated with the normal faults potentially, but obviously with a hydrothermal input.
Thank you very much.
Any other questions or comments? John, I don't see anything else. No one has their hand up, going once, going twice.
I would have a question, sorry, but I'm not sure how to put the hand up.
All right.
Okay, go ahead.
I just go. Yeah.
Hi, I have a question. Do you think, what do you think about overpressure, fluid-driven fault activity in such dead basins? Do you think there's place for that?
Yes, of course, yeah. I think that I've been presenting them as end members, almost saying, well, the fault is dead and it can valve. And then I say, well, the faults are pumping. But in fact, of course, you can have, if I have overpressuring, then all things being equal, if I was going to have a 3-meter earthquake, I might end up having 10, 30 centimeter ones. Yeah. So what the overpressure can do is it can effectively brings things to failure much more quickly and more regularly. And can get quite complicated dynamically then. Of course, the same thing is still happening. There's still fluids which are moving around, but they're within there's in this overlap where effectively there's a coupling between the fluids and the actual generation of the fault. In the end, though, the actual strains are probably very similar, whether it be a 3-meter fault or 10, 30 centimeter ones. The amount of fluids that potentially you could be pumping around are basically sort of very similar because the strains would be same. It's just you'd be doing it more continuously.
Thanks, John.
All right.
John, just a question from me, a general question on the sources of fluids.
Yeah.
I mean, that's particularly for the Irish ore deposits, for example. Is there a consensus of thinking on this?
The sources of the mineralizing fluids?
Yes.
Yeah. Well, there is, I think, I think most people subscribe to the view that the lower Paleozoics underneath these, like carboniferous limestones, are really responsible for the high zinc lead concentrations. It's probably not a coincidence that Ireland, along its length and along a lot of where all the mineral deposits are, is a suture zone for a basin that was 3,000 kilometers wide. And that's basically, that basin was consumed, but all the little bits which are in it, these sorts of terrains, are all actually straddling and going across Ireland. And most likely, because of where they would have been within a big ocean, they'd be rich in zinc and lead. And we know that a lot of the basement rocks are really similarly, they're really quite rich in zinc and lead. And then all we had to have, which is a happy coincidence, but it's not actually a coincidence, is the fact that if you take the crust and you stretch it across somewhere where there's an early stitch, an earlier orogenic belt, you will oftentimes localize the faults where that earlier structure was, the earlier orogenic belt was. And that's exactly what happened here. We stretch the crust north-south, we get these normal faults, and they're localizing really on what is the collision of a prior collision with all of these sweet bits of terrains in them. And the faults then start to mop up the zinc and lead, which derives from the little bits of pieces which were in this 3,000 to 4,000 kilometer wide ocean. So we're in a pretty special place, Ireland. So I'm glad to say it's much more united now than it was in the Cambrian. Yeah.
Any other comments or queries?
If anybody wants to contact me, they can get my email pretty handy enough if they want to ask me any questions. And if you are interested, just download the papers and give me a shout. Yeah.
John, with that, thank you very much for presenting this. I think it was an excellent talk.
Thanks.
Thanks again, and I hope
You're
everybody
welcome.
enjoyed it. Let's survive lockdown measures wherever in the world we are. Thank you very much.
You're very welcome. Thanks for having me. And if anything, it's kept you awake in lockdown. Some of you. All right.
Thank you very much.
Thanks
With
very
that,
much.
I'm going to end the meeting. Thank you very much.
Right. Bye-bye. See you, Craig. Good luck.
Bye. Cheers.
Bye-bye. Bye.
Thanks, John. Cheers.
Bye-bye. See you, Fiso.